Feature selection based on subpopulations and propensity score matching, a coronary artery disease use case using the UK Biobank. This study was resulted from a collaboration between MIT and IBM Research. I work for IBM Research since September 2016. So feature selection methods are very popular, very common in almost any domain computer science that incorporates data for a variety of reasons. And the first reason is to improve efficiency by discarding features that are not informative, that are not good classifiers, they are not good predictors. If you don't need certain features, why use them? Minimize the size of the resource required for the analysis. And if you can run your analysis using a smaller data frame and not a redundant data frame, this would be better. The algorithms are going to run much faster. It's going to be easier to transfer the data frame, especially if it's large, even with a smaller set of features. And to inform data collection design, for example, for clinical trials. For example, let's say that you want to design a clinical trial, you need to choose which features to collect and which features not to collect. It takes time and money, so it's better to collect as less as possible number of features that are necessary for the clinical trial. So we submitted our study to AMIA, and it was accepted, so I'm presenting it now. So the feature selection method is basically, that I'm describing is a new type of feature selection method that is very different from one another. It works very differently. And the way it works is described in the following slide. So imagine that you have like a big data frame of covariates and a binary outcome. The covariates could be of any type, categorical, continuous, and no missing values are allowed, so imputation might be required. So the method basically is based on some kind of a iterative process that runs many times. And in each iteration, a different subpopulation is being identified. A subpopulation contains positive patients who have the outcome, and negative patients. And those two populations are matched based on a small number of covariates, let's say 3 or 10 or 1% of all the possible available covariates. And they're matched based on propensity score matching. So these two populations, positive and negative, in each iteration must be very similar to one another. If you compare the values of the covariates that were used for matching. And when you do it in the same iteration, once you identify this subpopulation of positive and negative individuals, you basically look at the other covariates that were not used for matching, and you sort them by some kind of let's say, a descending order according to p-value or any other criteria. And basically, if a few of them or many address some kind of a predefined threshold, for example, p-values smaller than 0.001, then you reward these features that were not used for matching. And you repeat this process many times, and every time you reward features. And those that are getting the reward many times over time are the ones that are going to be considered as the ones that were selected. And then you can decide which ones you want to use. All of them, let's say the 10%, 3%, 3 top percent, and so on. So to demonstrate how well our method works, we used the UK Biobank. It's a database that became available for us, prospective study with over 500,000 individuals, including a variety of characteristics, almost anything you can think of that is available in EMR data, but also genetics related data and data that was gathered from questionnaires that the patients provided, and so on. And what's interesting is that a different group from the Broad Institute of Harvard and MIT published a study in which they used the UK Biobank It's about 173,000 individuals and close to 14,000 features to compare then their new feature selection method to leading other methods. And they came up with a new method that basically based on two steps that involves human in the loop. The steps are parameter optimization, then a clinical review to refine features that the feature selection method that is based on basically was not able to capture accurately. So those folks provided to us their data frame, and then we were also able to compare the performance and the advantages and disadvantages of our method to different methods that they applied and developed. So their method basically demonstrates that they identified 115 features, and you can see here the training, the performance on the training and the performance on the testing, and there is some kind of an upper bounded value that achieves the best prediction performance as measured by the concordance index, 115 features. And they applied this manual review to identify 51 features. So the maximal CI concordance index was 0.797. We took the same data frame, 173,000 or so individuals, and the same development and holdout sets that the Broad Institute folks used, and that contains a variety of features, anything you can think of, including genetics, and the same binary outcome, 10-year incident of coronary artery disease. And then we were able to apply our method, and I'm going to describe it more specifically in subsequent slides, and compare the results. And you can see at the top 4 leading feature selection methods, including the one that was developed by the Broad folks. And here at the bottom, you can see our method, subpopulation-based feature selection, with a variety of features. And you can see that our method was able to identify additional features on top of the 115 that improved performance by approximately 0.4%. And when you look at the pooled cohort equations, basically that's a widely used equation that is used by clinicians to assess a 10-year risk of ASCVD, which is basically it's an umbrella to different conditions like AMIA, heart attack, and stroke. And you can see that all of our methods, including those applied by the Broad and ours, provide a better prediction performance. So the method works like that. So you have a data frame, in this case 13,000 features, binary outcome, and 138,000 rows. That's the training set. So you choose a parameter, let's say an integer, 1% of all the available features, 138 in this case, and basically you also specify a caliper value that determines how close these covariates between the positive and negative patients is going to be. So how close the matching will be in each iteration. And then so once you chose these parameters, you apply propensity score matching, and keep in mind that each iteration you choose a random number of n. So each time there is a new subpopulation. And once you do it, once you match the cases and the controls in each iteration, you look at the other covariates that were not used to matching, and you sort them. In this case, in a ascending order, it could be descending order, and those that addressed a certain threshold value are being rewarded, and then you store them. You store the rewards. So in each iteration, you identify a subpopulation of cases and controls that were matched by a pre-selected number of features, and then you identify the features that were not selected, and you rank them, and you repeat it many times, and at the end of that, you basically get a list of features according to how well they ranked. And of course, many of the features of the 13,000 do not receive any rank at all. So we ran our method for 2,500 iterations. Why so much? It took about a week on a very powerful computer. And of course, there are opportunities to improve it further. And the method identified 510 features. Now, when you use these 510 features, the top 1, the top 2, the top 10, the top 500, the top 510, you see that using the top 141 covariates or features received the best prediction performance. And that's a little bit better than the results of the folks from the broad. If you look closer, if you look at the smaller number of features that were selected, you can see that even with a small number of covariates, you're able to achieve a pretty high prediction performance. For example, with 20 features, 0.792, which could be very useful. Here are the 20 top features that our method identified: blood pressure, being a smoker, HDL, genetics, and so on. I'm just showing it for an initial impression to see what are the features like. And they make lots of sense. See, demographics, physicals, labs, family history, drugs, hypertension, and they make sense because they're very consistent with the pooled cohort equations. So all of the components of the pooled cohort equations were identified by our method, and they're highlighted in green here, this slide. So the next step would be to evaluate different configurations of parameters, to evaluate convergence assessment. How many iterations should we apply? What is the performance if the number of iterations is very small? Then to find other use cases, not necessarily related to healthcare. And of course, what I wish is that people will give a try to the R package that we created. It basically describes the method, and I will be very glad to help other people to deploy and use it. So to summarize, we developed a new type of feature selection method that relies on propensity score matching. Our method has a couple of advantages. It has a comparable performance using a small number of features, comparable prediction performance compared to other leading methods. It achieves some kind of a boost in performance with an additional number of covariates that were not been able to identify by other methods. And the boost could be higher depending on the different number of iterations that we might apply and tuning. No need for manual review, and we have a package in R. So I wish that you contact me, and I will be very glad to help you to use the method in any use case in healthcare and beyond. Thank you very much. Take care.